So just a little while ago, maybe a half hour ago, I returned quiz. I know it says quiz 8, but it's actually quiz 7. And I wanted to just go over that quick. So if you haven't looked at it yet, it'd be good if you could open it up in Gradescope. Either way, I'm going to go over it. I'm just going to give everyone a second. You can pull it up. Returned in an email. Look at this. These solutions via Gradescope. Most might want to open it up. So here's the general idea on this first one. Concavity is determined by the second derivative, right? So second derivative being negative means concave down. That's like the upside down bowl shape. Second derivative positive means concave up, right? It's like a bowl. And so a graph is either one of those two things. And so a lot of people, when I asked you to label where it was one or the other, only put like a couple of locations. And you can see that the graph should be pretty well labeled. Because again, it's either concave up or concave down, or an inflection point. And so every time it switches from concave up to concave down, we need to put a star, right? So I was asking you to put a star on the inflection points, and you can see there's 5 of them because it switches in 5 different locations. So the easiest way to sort of approach this was probably just to look at it and think about concave up, concave down, and then you just put a star in between those locations. I tried to give about a half point, grading on this was about a half point per answer, although I tried to be a little flexible and, align your answers with your understanding. So anyway, just trying to say, let me know if you want me to clarify your own score or take another look at what you submitted. Be happy to do that. Any thoughts about this one? Can I clarify something about that? This is not the best quiz, just to be clear. So, be a good idea if people weren't clear about something that's going on here to let me know. What do you think? And you'll notice as you look at the Gradescope thing I returned, this is part of the answer. So you should be able to compare. I tried to circle a little bit where you got it wrong, and then you can compare it to the solution. On the second one, try to focus on what I wrote at the top here, this thing and this thing. All right, so I'm kind of giving you some points here on this graph, but then the way you're thinking about it is the first derivative tells us increasing or decreasing about the function, right? And with that in mind, the second derivative tells us increasing or decreasing for the first derivative, right? So every time you take a derivative, it tells you increasing or decreasing of the one before it. And so that's the way you're kind of thinking about this. And what I'm trying to show you at the bottom here then is like these two things are related to each other, right? So the function increasing means the first derivative is positive, or vice versa, right? If the first derivative is negative, that means the function's decreasing, etc. And then the things on the right are also related to each other, right? So concave down, for example, means that the first derivative is decreasing because the first derivative and the second derivative have the same relationship as the first derivative as the function. I think overall people did better on this one, so maybe this one was easier to understand or it looked more like the homework or whatever. So, but I did just want to clarify that. Again, they were worth about a half point each, and I tried to be flexible. Like if you said decreasing, but then you also wrote anyway. If your answers corresponded, I gave you partial credit. Is what I'm trying to say there. But are there questions kind of about this? I think the easiest way to approach this one was on the first one, kind of looking for increasing or decreasing, and then determining whether that meant the first derivative was positive or not. That just seems to be the progression that makes the most sense to me. Like, oh, at x4 is a flat spot. That means the function's constant, which means the first derivative is 0. Like that's the progression for me on the left-hand side of that. And you can think about it differently if you want, but just that's how I think about it. And then on the right side, I would think about like, okay, at x1, like x1, is that concave up or down? Okay, that's concave down, so I would get second derivative 0, right? So going from here to get this, and then thinking, okay, well, if the second derivative is negative, what does that tell me about the first derivative? That tells me it's decreasing. That's just how I would progress through a a quiz like this. But anyway, I'm happy to clarify anything I've said there. Wanted to just ramble for a minute and give you a chance to look at your own quiz. So there are only things on your own quiz you want to clarify? Anything I said?
At x3, why is f prime increasing?
Because these two things are related to each other. So the derivative, were you thinking it was 0? Is that what?
Yeah.
So
That explains it though, the concave.
yeah, the
Explains it,
concavity, I'm
yeah.
trying to maybe how to rationalize. I also see I have a typo there, I should say, with a T. Those two things are related to each other. So yeah, what would the derivative being constant mean? I think that's the thing I would like to clarify. So the derivative being constant, I'm going to write it down at the bottom. F prime being constant would be in something like when we have a straight line. So like 4x plus 1, and then you take the derivative and you just get 4. That would be an example of the derivative being constant. And so we get constant derivatives when we have a straight line. And I agree that it's a little confusing, like, oh, isn't it 0 there? Like, yeah, right at x3, it's 0. I agree. So if we kind of zoom in on the spot, f prime of x3 is 0, but the derivative itself is increasing because the second derivative is positive. And so they're kind of two different things there. And I totally see what you're saying there, and I agree that's a little bit confusing. But the idea is, it's like the derivative is negative here, and then it equals 0 here, and then it's positive there. And so you can see it's increasing, right? It was negative, it became 0, and then it's going positive. And so all those things are indicating that the derivative is increasing. And so it's 0 at that point, but it's still increasing, if that makes sense. Yeah, thanks for that clarification. I think that was a good one to look at. Did people see what I'm saying there? Or can I say something else about that? Yeah, it was a good clarification. Other sort of things like that could be more basic. Oops, I see something in the chat here. Sorry. Can we go over the 2 inflection points in the top max? So on this problem you're talking about, Sebastian, or on the first problem? I think maybe you're talking about, I'm talking to Sebastian here. I think maybe you're talking about these two things. So then why is x1 prime? Okay, so you're talking about this one. Okay, so now you're talking about maybe this piece right here, right? Okay, so two things. So first of all, I think first you're talking about right here. And so on this particular piece, the second derivative is negative because it's concave down. Right? On this entire piece, the whole piece is concave down. And so that automatically is going to imply that the first derivative is decreasing. Because if we think about what the tangent lines look like, the tangent line right here is sort of kind of steep, but the tangent line right here is less steep. And as we move along this curve, it's becoming negative, right? So like over on the left side of that peak, we had a positive tangent line. And then on the right side of the peak, it became negative. And so that's showing us the derivative is decreasing. Hopefully that makes sense. So the thing I'm really trying to get across here that I've wrote in the words right here that I would refer to back to if you're trying to look at this later is the first derivative tells us increasing, decreasing about the function, right? So when you take a derivative, it tells you increasing, decreasing. And so if we take a derivative of the first derivative and it becomes the second derivative, that tells us increasing, decreasing about the first derivative. I know that's a little confusing and I say the word derivative a bunch, but that's the sort of thing I'm thinking about. So to your other question then about the one up here, let's look at this in three pieces. We've got clearly concave up there and concave up there, right? I hope you can see where I've just highlighted in green, definitely concave up. So the second derivative is positive, right? And in between those, it's definitely concave down, right? And most people got, if you only labeled like one thing on this graph, most people labeled that top peak as being second derivative negative, right? Because it's concave down. And so hopefully you can see, just kind of zooming in on that peak, it changed from concave up to concave down. If it changes, that by definition is an inflection point, right? An inflection point is where it changes concavity. And so I know it's kind of a tricky one because it's not a flat spot, but if we just kind of look, again, I can zoom in real close there, right? It changed from bowl shape to upside down bowl shaped and then back. And so there's got to be an inflection point between those spots. Does that clarify that one for you, Sebastian, or anyone else? Anytime it changes concavity, it's an inflection point. So again, the way I would progress through this one would be, I first labeled the spots concave up or down, and then I realized, okay, between each one of those has to be an inflection point. And so then I put a star. And you see, I put a sun there, right? Sun's a star. So funny. What a guy. Clarify that though. Did I clarify something else? Okay. This is the kind of, the interpretation that's relevant and important to the optimization problems and things like that, for example, because we're trying to figure out a max and the, relates to concave up or concave down or the first or second derivative test. And so this is just sort of that type of interpretation. All right, I'm going to keep going here if there aren't any other questions. For some reason, there is a weekly schedule. I uploaded it, but every time I try to open it, it just shows me the one from last week. I did put a new weekly schedule up. For some reason, my Google Drive is not updating. I don't know why. Let me just see that one more time. If I can go back, refresh. Like when I open it on my computer, it's different, but when I open it on my iPad, it's the old one. It's very strange. Anyway, so I can't show you that, but there's homework due tonight. So I extended that homework from last Wednesday or from last Friday to tonight. It was the optimization homework. And I have not actually gone through and see where people are at with that. I don't know if people wanted to talk quickly about that. I really don't want to, I spent the entire class period, on Friday, kind of setting up a lot of those problems. If you have some quick questions about that, we can look at that. Otherwise, I really would like to keep going with the material today. People okay with that homework? And kind of quickly. Okay, I have office hours this afternoon. So if you're still stuck on some of those problems and you want to talk about them because they're due this evening, let's work on them in office hours. Come on by. But I would like to keep going with implicit differentiation and related rates because implicit differentiation is one of the homeworks that's due on Wednesday today, this week. So implicit differentiation is related to related rates, which is why we put them together. And just to be clear, this is what we're doing on this page. And then the next page is related rates. So this entire first page is implicit differentiation. And it's the kind of thing that we already know how to do, but the notation and the interpretation sometimes can be a little bit tricky. And so that's what I really want to focus on this page. And then we're going to apply this concept on the next page in really interesting ways. And so this is another kind of culmination, in my opinion, the optimization stuff, which is due tonight, and then this related rate stuff, which will be due next week, is kind of the culmination of all the the derivative stuff we've done. It's like we learned a bunch about derivatives, and now we're going to apply them in these two interesting ways. And so before we do that, we got to learn a little bit about implicit differentiation. And so let's, the word implicit is the confusing thing about that statement, that description. And so let's talk about the difference between implicit versus explicit, right? So if someone says something explicitly to you, they're being very clear about something, right? But if someone implies something or says it implicitly, they're being a little more vague and they're kind of directing you towards it, right? So that's one way to sort of just think about the way those words or what those words means. I mean, but with that in mind, in mathematical speaking, an explicit differential or explicit function, like it says right here, very clearly writes the dependent variable on one side of the equation and the independent variable on the other. And so we usually think of the independent and dependent variables as y or f being the dependent, and the independent is the input. And so that's usually x or t. And so it's most equations we've seen and most equations you're familiar with are explicit. For example, let's do a couple examples here. An explicit equation, an explicit polynomial, for example, might be y equals x squared minus 4x plus 6. And that's explicit because the dependent variable y is on one side and the independent variable, in this case x, is on the other side. And they're not mixed up. They're on either side of the equal sign. Or how about some f function? So sometimes you write the dependent variable as f, right? So f of t equals square root of t squared plus 4 or something like that. Right? The f is on one side, the t is on the other side. Or we can do y and t's as well. So how about something like y equals t squared minus 1 over t squared plus 1. Like the thing I'm really trying to point out here in all these examples is we have the y or the f on one side and the x or the t on the other side of the equal sign is what I mean when I say sides. And we've certainly been dealing with these kind of functions so far in this course, because then we differentiate like dy dx or something, and you get y prime on the left, and then you use the rules on the right. And so these are the most of the problems we've seen so far. Just in most math classes in general look like this, but definitely in this course, they've all looked like this so far. Implicit is when you have the variables kind of mixed up on both sides. And so like it says, an implicit function is an equation in which the dependent variable has not been defined in terms of the independent variable, right? So again, we're thinking about the dependent variable as being either y or f of x. And so we might have those mixed up in an equation. So maybe something like this. We have like y cubed plus y squared t minus t cubed y equals 3. And so we're still thinking about the y as being the dependent variable. It depends on the t. But now it's all mixed up, right? We have the y's and the t's are sort of together on one side of the equal sign. Let's write another kind of example. How about look at the examples I've got written down. How about yt plus t over y equals 6. That's an implicit function. An implicit function we see in pre-calc would be the unit circle, right? X squared plus y squared equals 1. We see that in pre-calculus. That's the equation of the unit circle. And the x is the independent variable, y is still dependent, but they're both on the same side of the equal sign. And so the thing that sort of the takeaway here, the thing that all these things have in common is that the input, which is either t or x, and the output, which is either y. In this case, I'm just going to stick with y probably. They're on the same side of the equation. And there's nothing we can do about it. Like that's kind of the key thing too. It's not just that, oh, they're together. But if we could separate them, that would solve the problem. And in some of these problems, and I'm just kind of looking at the ones I chose, trying to remind myself, yeah, all these problems I chose, you can't actually separate them, right? So the input and the output are on the same side of the equation, and you can't isolate them. So we can't explicitly solve for the y. And so there's no getting around it. We have to think about what to do if we want to differentiate this. Let me just pause there and see. This is mostly a notation or like conceptual kind of thing so far. We're obviously going to look at some examples in a second. But do we kind of see the difference between implicit and explicit? Sure. In my first example of explicit, I was using F's and Y's. Moving forward, we're only going to use Y's. And I believe the homework only uses Y's as well. I just wanted to be clear that sometimes we represent outputs with F, and I'll kind of talk about it a little bit in the next step, but you can see all the examples at the bottom only have Y. So we're not going to talk about F really. But the idea is, and what we're about to look at is, even if we can't solve something explicitly, these implicit equations, we still want to think about them in terms of those independent variables. So for what it says down here, I'm about to sort of move into this section and summarize that. It says we can't actually solve for these things explicitly. And so when we differentiate them, we want to think about them as still being functions of t. And then usually use the chain rule. Oftentimes we use the chain rule to differentiate these things. So for example, if we just had like, let me just do a very basic example. Let's say we had y plus t equals t squared or something like that. And let's say we wanted to differentiate that. So let me just do a kind of a mini example right here. So if we did d over dt of both sides, we're still thinking about y as a function of t. And so what happens here is we end up with y prime, or dy dt, plus 1 equals 2t. Right? And so this is the implicit part right here. This is y prime, right? Because y is a function of t. So when we differentiate it with respect to t, it just becomes the derivative. It's like we know there's a t in there somewhere. We don't know exactly what the explicit representation is, and so we're just going to write it as y prime. But the other two things, these were just power rules on t's, right? Because we were doing d over dt. That's sort of the general idea. It's when we differentiate the independent variable, we just use the rules. When we differentiate the dependent variable, we need to use this implicit differentiation idea. Okay, so we're going to look at several examples here, but that's the general idea. Are there questions about what I'm trying to say there? Maybe you want to see an example before you formulate a question, but can I clarify something so far? These are the kind of questions that are in the homework for this week on Wednesday. So there's homework due tonight that was from last week that I've extended, et cetera, et cetera. And then there's homework for Wednesday that's based on this. And these are the instructions usually. It usually says, sorry, I'm pretty sure the instructions, come on, iPad, you can do it. Okay. The instructions say, hey, use implicit differentiation to find the derivative, y prime. right? But the way you want to think about this is now a notation thing. Let's kind of be clear about this. dy dt, right? This is the derivative with respect to t of y. And so that's how we're thinking about y prime now. And so let's look at this first example here. And I zoom in on this one and kind of slide it over. Great. So it's implicit because we've got t and y on the both on the same side, right? We don't have something that says y equals. And the way we're thinking about this is y is a function of t. And so really thinking about this like this, right? It's like y of t squared. And so if we differentiate this, this is going to end up being a chain rule. Because we're doing d over dt. If we were doing d over dy, it would be a power rule, but we're doing d over dt, and we're assuming y has some t that's hidden in it, like it's a function of y, but we don't know exactly what that explicit function is. And so we're going to implicitly assume it has a t in there and use the chain rule. That's sort of the general setup on this first one. I'm going to try to do this first one pretty slow here, but let me know if I can clarify something as we go. So that's sort of the general setup. And so let's do it. So we're going to do, switch colors here. We're going to do d over dt of the first term. We're going to do d over dt of the second term. And remember, I'm not going to write the of t just to save us some space here. But remembering that y has a t in it. And then we're going to differentiate the 6. And we're thinking about this as a power rule. This one's a chain rule. And this one's a constant rule. And it has to do with the fact that we're doing d over dt, right? So this is where the notation comes in and is important. We're differentiating with respect to t. And so for t squared, just as a power rule. But when we do d over dt of y, y has a t in it that we can't see. And so that's where it becomes a chain rule. We're differentiating a function at that point, right? And then when we do d over dt of 6, that's just a constant rule, and 6 can become 0. Let me just pause here and see if that seems okay so far. So, okay. Let me just do the chain rule part of this over here on the side. We can do the details. I'm going to do the details just one time. So this is a chain rule with the outside function being 3x squared and the inside function being y. And just to be clear, it's y of t. And so f prime is just going to be 6x, but we want f prime with g plugged in, so that's going to be 6 times y. I'm just kind of thinking through the chain rule. I'm just going to write the details down just one time to kind of think about how that works. And then when you differentiate the g part, it just becomes y prime, right? So g prime is just y prime. And so then the full-on chain rule then, if we did like f prime of g times g prime, that's going to be 6y times y prime. And so this ends up being the derivative of the y squared part, the 3y squared part. Right, because we're doing d over dt. And I didn't write that down, but maybe I'll just do this. Recall, we're doing d over dt when we do all these derivatives. And so that's why this turns into a y prime. And so then the next step in the derivative itself, right, we do a power rule, so it just becomes 8t. We just figured out that middle derivative part. That middle part became 6y times y prime, because it's a chain rule. And then the constant just became 0. And so you can see we're going to be able to find an expression for the derivative. We can solve for y prime to get the derivative here. And so let me just pause though, because this is we've done the hard part. We've done kind of the confusing implicit differentiation part.
I have a quick question.
Yep.
How do you know, like, how do you know that y isn't just a variable like t?
So y we're always thinking about in these problems as being the dependent variable, which means we're assuming it's a function of t. So in all of these problems, all the ones on this page, all the ones in the homework, I can just double check the homework too to be sure. There's y's and t's, and y is a function of t. This is how we're always thinking about this right here, this part right here. We're thinking about not just y, but it has a t in there. So when we do d over dt, we need to think of it as a function. And let me just make sure I'm just going to page through a couple of the homework problems. I'm pretty sure they're all y's. There are some x's. There could be y's and x's. I put an x on this one. No, I did y's and t here, but sometimes they're y's and x's. Okay, mostly y's and x's. And so the key thing that we're kind of, when we're looking at this, maybe the original expression, we're doing d over dt on all these things, right? And so d over dt of 4t squared is just a power rule, because it's saying, hey, the variable's t, and look, there's a t squared. How do you do a t squared variable derivative, excuse me, when they're differentiating with respect to t? Oh, that's just a power rule. But this middle term, when you do d over dt of y, that's a different thing, right? And so it's like, whoa, well, how does that match up? Well, if it's a function itself, the way we're thinking about this, it's like there's a t in there somewhere, we just can't see it. And so we're just going to assume there's a t in there and use a chain rule is the way we think about that.
Okay. Thank you.
And we'll see a common thing happening. So basically, anytime the dependent variable like y is being squared or raised to a power, we're going to use this same kind of chain rule idea. Can I look at another one, or can I clarify this one first? I'm going to do the one right below it, which is a little more complicated. And then I'm going to ask you to think about the one on the right, which is very similar to the one we just did here. So hopefully the next one will ramp it up a little bit. Maybe it'll make a little more sense. And then I can think about that other one. Can I clarify something before we do that? Okay, so let's do d over dt of this next one here. So I'm going to do d over dt, but this is a y of t. And so that's going to end up being a chain rule. I'll write that down in a second. We're going to do the derivative with respect to t of this. That's going to end up being a product rule. And then we're going to do d over dt of this, which is also going to be a product rule. So I'm just kind of thinking about these separately. This one's going to be chain rule. These two are both going to be product rules. Right? Because we're multiplying two things. One of them is a t or a t cubed, and the other one has a t in it. I forgot to write that. So let me make that quick note here. This y is a function of t. And then the last one is just going to be a constant rule because it's just 3. So we're going to get 0. Oh, I forgot to finish the last problem too. I'm sorry. Darn it. Should have finished that last one before I went on to this one and then messed it up. So it's still on that page. So I'm just going to just realize how I had so much room on this last one. I'm going to finish the previous problem. So I apologize if you're still writing this down. Let me just pause and everyone finish writing that first part down. Because the question on the last problem is, let's find the expression for the derivative. Let's use implicit differentiation to find y prime. And so in that last example, we have y prime in there. So let me just zoom in on this last example. We have y prime, and we can just solve for it. Right? Y prime is currently in that expression. So let's just get it by itself. And then we'll have something that says y prime equals, and that's the derivative. Right? So we can solve for that pretty easily by subtracting the 8t to the other side. 6y times y prime equals minus 8t, right? And then just divide by the 6y. So y prime is minus 8t over 6y. And so that's an expression for the derivative. It's in terms of the function itself. So it's not a typical derivative we're used to seeing. So again, it's implicit, right? We have the t's and the y's mixed up on the same side, but it's an expression for the derivative. And you'll see how this becomes useful once we start using it in the on the next page. It's just a different way to approach a problem that's represented implicitly. Sorry about that. Forgot to finish that one off. Is that okay? Or are there questions about how we're starting this next one? I hate to bounce back and forth like that, but okay. So when we take these derivatives with the chain rules, right? So this chain rule right here with the y cubed, and then we're going to have another chain rule inside this product rule. Those two ones are going to be very similar to the chain rule we did on the last one, right? It's a chain rule with like a y that's being raised to a power. And so we're going to think about it as bringing down the power, doing like a power rule, but then multiplying by the derivative on the inside. In other words, it's going to end up looking like this kind of thing. Right? That's how we're thinking about these. And so I'm not going to write all those details. Let me know if you want to see them, or I can talk about them a little more carefully here. But this one, for example, right, this first chain rule becomes 3y squared times y prime. That makes sense. Very similar to the last one, how it was 6y times y prime. Bring down the power, subtract 1 off the power, but then you need to multiply by the derivative of the inside. Right, when we do the first product rule, I'll write out a little bit of the details we're going to do. F prime g plus f g prime. So that's the first product rule. And then the second product rule looks like this. F prime g plus f g prime. And then the constant just goes away, right? It just becomes 0. How does that look? Seems okay.
I think we're
Between the
supposed to
two,
subtract those two.
yeah, between the two product rules, you got to subtract.
Thank you very much. Does everyone see that? This turned into a plus for some reason. It should be a minus. So let me delete that. Thank you. Anything else seem questionable or clarified? And so inside each one of those product rules, then we're going to have another, we have other derivatives to take care of, and they're either a chain rule, so this is another chain rule here, or the power rule. The last one's not either of those things, right? We're just doing d over dt of y. This is just dy dt, which is just y prime. Right? It's not a chain rule. It's just dy dt. So when you have just y raised to the power of 1 and you take d over dt of that, it just becomes y prime. So we get, a similar looking expression that we'll be able to solve for y prime with, right? So this first part didn't change. We do the chain rule on that other piece, and it's going to become 2y y prime, right? D over dt of t just becomes 1. So here's that first product rule kind of repeated. Hopefully that looks okay. And then the second one will become 3t squared times y. And then we just do y prime on the second piece. Let me know how that looks. And we want to solve for y prime. That's the next step, but I want to see if there are any questions here. We're not quite done, right? We want to solve for y prime, but let me see if, this is the important kind of confusing part, right? And if this is a test, you get 90+% of the points for getting this far. And then if we want the expression for y prime, that's how we finish it off. Questions so far, though? So in my notes, I feel like there should be a question. I don't know if people are still writing or not, but does that seem all right?
Yeah, I guess I'm just a little confused. After taking the derivative from the product rules,
Yep.
I guess my question would be, why are we taking a derivative of that again on the next step?
So this, if I look at this piece right here, we're trying to take this first derivative of the whole thing, right? And I'm recognizing as this having a t, this being a t, and so we're doing d over dt of two things that have t's in it, right? So that's what makes it a product rule. And so when we do the product rule on this, this becomes this. And now we actually need to do those individual derivatives, right? So the first derivative, it's like, okay, this is going to be a product rule. And then I'm saying, what's the product rule look like? It looks like this. And then when we do that, you need to actually compute these things, right? You need to do like this one and this one. And then we, just like we've done before, it's like, okay, we recognize as a product rule. I'm kind of writing out the details of the product rule and thinking about what do those individual things look like. On the first one, I know y is a function of t, and I'm doing d over dt of it, so that's what makes it a chain rule. And on the second one, if I'm doing d over dt of t, it's just a power rule. And so that's how we're breaking it down. I'm trying to write out all the details. I don't know, maybe that made it look more confusing. I'm not sure. Does that clarify it?
Yeah, it does. Thank you.
Other things like that was a good thing. The last step here is to get y prime by itself, and it's in a bunch of places, and so it's just algebra, quote unquote, just algebra. I know that can be confusing, but that's not like a focus of the course, I guess, is why I would like to make sure this first part looks okay. So I'm gonna just do this in 2 steps. I'm gonna get everything without a y prime, and I'm going to add it to the other side. And I'm going to keep everything with a y prime on the left. Right, so like 3y squared, y prime is going to stay because it's got a y prime. 2y, y prime t is going to stay because it's got a y prime. I'm going to move the y squared to the other side. And I'm going to move the 3t squared y as well, because it also doesn't have a y prime. And then this one is going to stay. And so I'm keeping all the y primes together, because now I can factor out a y prime. Feel okay about that? Because now I see there's a y prime, y prime, y prime. So I can factor that out. And then we'll just move it over to the other side to get y prime by itself. Right? And so if we want a solution for y prime, we want an expression for the derivative. That's just what we had on the right divided by this piece on the left that we just factored out. Right, so we just factored these out right here. What do you think? It's all right. This is what's in the homework on Wednesday. There's a bunch of these kind of problems. And I would like to look at some on Wednesday. There's a couple I have in mind in particular, but I would like people to at least have a chance to look at the homework before we do that. For what I'm seeing, no one has started it. Well, one person did a problem. One else has. So, look at it for Wednesday. Other thoughts about this one? This is a kind of a hard one. This is looking at the homework. This is the level of difficulty that exists in homework, I would say. Okay. So if there aren't questions, you feel all right trying this last one here? So we're gonna do d over dt of this last expression. Right, so we're gonna do d over dt of both sides. So it's gonna be like this. And there's nothing in those three terms that we haven't seen so far. Right, we got a power rule, chain rule, and a constant rule. And so what we want to try to do here is, so the instructions, find y prime. Find an expression for d, y, dt, which is y prime. So do the exact same thing we just did. It's going to be chain rule, power rule, constant rule, right? Just spend a couple minutes, think about that. Kind of compare it to the ones we just did. I don't know if people want me to zoom out so you can see it all. Hopefully you wrote this down yourself, but there it is in case you wanted it all on the screen. And let's just take a second and try that. So I do want to let you finish this one off, but just in case people are a little stuck here, just to get us started, right, we want to do, it's all in the notation, right? So d over dt of t cubed, so that's the variable itself, so that's a power rule. But on the second one, d over dt of y of t, we know that there's some function with the t there, and it's being squared, and so that is a chain rule. And then the last one is the one where we get the constant rule. Just want to do that same kind of thing we've been doing in the last couple. Just gonna wait another minute or so, or if people want to clarify something, let me know. But that's what we're thinking about here. What are the details of the chain while you guys are working on that, in case anyone's still confused about that? So that's a chain rule with the outside function being x squared and the inside function being y. All right, so there are the details. Let's finish this thing off. So the power rule on the first one just becomes 3t squared. When we do the chain rule, we'll get 2y prime. Right, that's the thing that we've been seeing a couple times right now, right? This is my f prime with g plugged in. This is my g prime. And then the constant rule to the 4 just goes away, becomes a 0, right? And this one's not too bad. If we want to get y prime by itself, just divide the 2y over to the other side. And so 3t squared over 2y is y prime. So I've got a little bit of room here. And so let me just finish this one off by doing one that looks like the homework. So a couple of the ones in the homework look like this. It might say, let me look at the way that they phrase it. It specifically says like, find the slope of the curve at some point, at the point, say 1, 2. And so what this is telling you to do is it says, find y prime with the point 1, 2 plugged in. Right? Is it clear that's what it wants us to do? Right? Slope of the curve is the derivative, and at 1, 2 would be the point you plug in. And the difference here is usually we just plug in like that one variable in, like the x or the t. But now there's a y in the expression, and so we need both those points. Right? This is our t, this is our y. And so this would be then y prime is 3t squared over 2y. We just plug those numbers in and we'd have 3 times 1 squared over 2 times 2. Right? So 3 over 4, just as an example. Right, so it's taking it a step further and just plugging points in. So there's a couple that kind of look like that. Like number 5 says that. The numbers are messed up on this one, unfortunately, but 5, 15, 17. Right, that's the kind of idea. Anyway, we can look at another one of those on Wednesday, but I'd like people to maybe have a chance to look at the homework first. Questions about this? I want to just finish by looking at the application and related rates. We'll just do one example on the next page, and then we'll save the rest for Wednesday. But are there thoughts about implicit differentiation? So I hope you're asking yourself, like, how does this ever come into the real world? And I remember thinking that learning related rates, like, when would we ever have this function that's inside the other function that has an implicit variable? Like, how does that even work? And so it works, or it comes up when you have an equation where something in your equation is itself is changing. And that happens all the time when we're thinking about applications. And so I put 2 on the next page. I'm going to look at the first one here, and then we'll do the second one on Wednesday. But in both these applications, if you want to read the second one, for example, we have a situation where we can write down an expression and something in the expression is changing itself. And so this is the related rates page. I mentioned on the last page that this would be related rates. And this is actually a problem that's from my pre-calc class. If you had me in pre-calc last semester, we saw this in the composite section. And so I'm bringing it back to learn a little more about it. So let's say we had a bunch of rabbits and they live out in our woods and they approximately live in a circular area. And if there's, good times with lots of food, they expand their population and the area gets bigger, right? So the population grows. And in bad times, maybe, like there's a lot of wolves around, there's not a lot of food, the population might shrink a little bit, and so they might condense into a smaller area that they occupy, right? And so the idea is, if we want to know where they live, like the area they live in, it's a circle, and so we know the equation of a circle, pi r squared. And so, but the radius is changing itself. And so that equation, the radius is a function of time, right? And so that's what the second piece says. So we know the equation, but the radius is changing, right? It's changing over time, where t is years. And so we have this function. So the first question says, write an equation that expresses how the area is changing over time. We know what the area is, right? We know that a is pi r squared, but r is a function of t, and so that means a is also a function of t. Right, and so this, let me actually rewrite the last part. The last part then is an implicit situation, because we have the radius, which is itself going to be changing, right? And so this is exactly in a situation where we have an equation, but something in the equation is also changing. And so we get this implicit differentiation part. We don't know what the expression for r is. We just know that it's changing over time. And so it's a function of time. And so if we were going to try to differentiate this, do d over dt like we have been, it turns into the same situation, an implicit differentiation with a chain rule. All right, so the next step here, let me zoom in a little bit, is to do d over dt of both sides. And we're going to end up with a chain rule on this side. Just like we did in the last problem, right? Y squared became 2y prime. Well, r squared is going to become 2r prime, just like we just did a second ago, right? So just in case we need to see this again, right? The outside function is x squared. The inside function is r of t. Okay. And so that means f prime is just 2x. F prime with g plugged in is just 2r. And then g prime is r prime. We just get 2r prime, just like we have a second ago. It's no different than anything else we saw on the previous page. We just have a little bit of context, right? And maybe I should have been more clear about this, right? We're trying to find an expression with how the area is changing over time. And so this is telling us to find a prime of t, right? Which is d over dt of a. I should have started with that. That's why we're doing d over dt, because we want to figure out, how is this changing? We might really care about this if we were rabbit hunters, or sometimes people think rabbits are a pest if they're a farmer or something. We might want to know how this population is changing. And so we now have a way to figure that out. All right, so let's take our work from the previous side there and continue it. So we have dA dt on the left, and we get our chain rule on the right. What do you think? Does that seem okay? Questions about the implicit differentiation at all, or the problem set up, anything like that, what I'm trying to say there? And so, once we have an expression like that, we can do interesting things like it, like this next question, for example. So let's say that at t equals 2, let's highlight the relevant parts here. So at t equals 2, so 2 years after this process started, let's say the radius is 50 meters. So that's telling us the radius value at that time. And it's telling us the rate of change at that time, right? So this is telling us at t equals 2, the radius is 50. So r of 2 is 50. That's the first thing that we're being told. And then the second thing says it's changing at a rate of 2 meters per year. I don't know why I keep writing f. That means r prime of 2 equals 2. Right? Find a prime of 2. How is the area changing 2 years after based on this information? That's really what we're trying to figure out here. A prime of 2 would tell us how the area is changing at t equals 2 years. Is the area getting bigger, i.e. is the population getting bigger, or is maybe the population getting smaller? And so we just plug all this stuff into our formula, right? We want a prime of 2, which is pi times 2 times r of 2 times r prime of 2. And we have all those pieces of information. Right, we just plug them in. So we'll have pi times 2 times 50 meters times 2 meters per year. And I'm including the units there because ultimately we want to have some good units on our answer. And so if we just put them into the problem, you can figure out what the final ones end up being. And so we multiply those things together, like 2 times 50 times pi. We just get, where it happened here? I'm missing something. Oh, that's right. 2 times 50 times 2 would be 200. And then 200 pi meters squared per year, which is approximately 628 square meters per year. Right, and did the units make sense there, right? So this is how the area is changing. And so area would be meters squared. And then the changing part gives it a rate. And so it's meter square per year. Right, so it's area per year. And the way, again, the way we kind of come across that is because when you multiply those two units, meters times meters per year, the two m's multiply to give you the squared. So sometimes people get a little confused with the units, and I'm just trying to point out, if you just put the units right into the problem, they take care of themselves. What do you think? Clarify something there? Okay, I'm not going to dive into the next one because it's a little bit involved, but I thought maybe I would just do one of the homework problems or something like that. Got the time, and I think it would be helpful. Can I clarify something about this question before I maybe just pull one of those up? So let's go to the homework. Just looking at this one, for example. And let's look at that one. So this one has y's and x's, as I mentioned before. And so we want to think about this as still y being the dependent variable, i.e. y is a function of x, and x is the dependent variable. I'm sorry, independent. So we want to think about y. This is like y equals something with an x in it, but we don't know what the explicit expression is, right? And so we're going to do, you can see the answer here. We want the answer to be y prime. So we want something that says y prime equals blah, 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 just like we've been doing. And so we're going to take our expression and we're going to do d over dx of it. Right, so we're going to do d over dx of the left side and d over dx of the right side. And so it's going to end up, let me just write out the details here. It looks like this. And this also has a trig, obviously, so hopefully this is a little helpful for that, right? So it's all in the notation, right? So d over dx of sine of x, this is just the sine rule. But when we do it with the cosine part, right, d over dx of cosine of y, that becomes a chain rule. Because you have the y, you have the function inside the cosine. And then on the right-hand side, we're going to end up with a product rule, where the individual pieces of the product rule are going to be the same thing as the individual pieces on the left, right? And so let's keep going then. So the sine rule just becomes cosine, or sine is cosine, yes. The chain rule on the middle piece becomes, so cosine turns into minus sine, and then you do the derivative of the inside. Right, that's the chain rule. And then the product rule, how does this look? I have a ton of room. Let me see if I can squeeze it in. So f, it's going to be the individual pieces that we just looked at, right? So f prime g plus f g prime. Apologize, I'm running a little bit out of room there. Let me zoom in a little bit. So that's the product rule. I would describe that as being the hard part of this problem. The rest of it is algebra, which is also, I don't want to say that's not hard, but this is the important part, I would say. This is the implicit differentiation part, the stuff related to calculus. The next part, the algebra part, is still important. And if you want to get this question right in the homework, you need to be able to do that. But it's, if this is a test, I would feel really good if you got this far. Because now we just want to solve for y prime. Questions about the implicit differentiation at all? Okay, there's only a couple minutes left, so I just want to finish this one off. The way we solve for y prime is you want to get the y primes on the same side and get everything else on the other side, right? So this has a y prime in it, and this has a y prime in it, and so we want those to be on the same side so we can factor it out. And the other two things, this and this, are going to be on the other side. So I'm going to show those intermediate steps here, but not all the details. So this can be, will then be, let's see. So how about cosine x minus cosine x cosine y? I'm going to add the thing to the other side, right? So it's going to be sine y times y prime I think that's what I was going for. And then you can factor out this, the y prime, which is why we did that, right? So factor out the y prime, add it to the other side. Oh, I had more room than I thought. Okay, I don't need that other page. So this side stays the same. I'm going to factor out the y prime. And if we want an expression for y prime, we just divide that stuff to the other side. All right, that's all I've got. I'm happy to stick around and answer some questions. I will put this one into the homework folder. We can look at some more on Wednesday if you want, but I'd like it to be driven by your questions, so you can let me know which ones you want to look at. And let me know what you want to see about this one. Questions about this one? All right, I'm going to hang around if you need anything, but otherwise that is all I've got for today. Thanks, everyone.
Thank you.
Thank you.
I see that question. How'd you go from minus sine to cosine x? Let's see here. I'm thinking, Sebastian, you might be talking about this step right here. Is that what you're talking about? So I grouped the things that were together. So the things that are highlighted in yellow ended up on the same side, and the things that are highlighted in red ended up on the same side. So this went right here. This is right here. And then this is right here. This is right here. And I did that because I'm trying to get the y primes on the same side and things that don't have a y prime on the other side. And so I know it's looking messy, but the point of that was then because you can factor out the y prime, right? So we had a y prime here and a y prime here, and then we factored it out so that we could get it by itself. We want to get it by itself, so we tried to group them. All right, I'm glad that makes more sense. Gregor, got anything else? All right. I'm not sure if you're still there, Gregor, but I'm going to sign off unless I hear from you here.